Good morning, everyone. Today, I would like to discuss the topic about wireless sensor networks. Recent technological advances allow us to envision a future where large numbers of low power, inexpensive sensor devices are densely embedded in the physical environment and operating together in a wireless networks. Mainly, the wireless sensor networks are mainly useful in the first in the US National Research Council report titled like this. It will be embedded with the processor. Mainly, we can use the wireless sensor networks in different environmental sectors like health monitoring and environmental contaminant detection, industrial process control, and military target tracking. Here we have different types of AASN networks. Mainly the AASN network can be considered with the different types of the equipments. What are those equipments inbuilt with the AASN? Mainly we have in that sensors is placed and memory is placed and power is placed in the wireless sensor devices. Mainly, it will be equipped with the low power embedded processor. The computational tasks on a AASN device include the processing of both locally sensed information as well as the information communicated by other sensors. This is the main schematic diagram of the AASN device: sensors, memory, processor, GPS, and radio transceiver. Coming to the memory, storage in the form of random access and read-only memory includes both program memories and data memories. Actually, this WSN storage will be taken place in random access and read-only memory, which has the both program memories and data memories. The quantities of memory storage on board a WSN device are often limited primarily by economic considerations. Due to some of the economic consideration, we can go for the RAM. So because of the random access memory, we are using only for the temporary purpose, but for the RAM should be the permanent data that should be useful for most of the devices. So that is coming to the radio transceiver. WSN devices includes a low rate short range wireless radios. And coming to the sensors, due to the bandwidth and power constraints, WSN devices primarily supports only low data rate sensing. Many applications call for multimodal sensing. Coming to the geopositioning system, in many WSN applications, it is important for all sensor measurements to be location stamped. The simplest way to obtain positioning is to pre-configure sensor locations or deployment. But this may only be feasible in limited deployment, particularly for outdoor operations when the network is deployed in an ad hoc manner. So, mostly that information is mostly easily obtained via the satellite-based GPS. Coming to the power source. For flexible deployment, the WSN device is likely to be battery powered. Coming to the applications of the wireless sensor network, the several envisioned applications of wireless sensor are still very much under active research and development. Mainly, it will be applied mainly in the ecological habitat monitoring. Scientific studies of ecological habitats are traditionally conducted through hands-on field activities by the investigators. One serious concern in these studies is what is sometimes referred to as observer effect. Then, coming to the military surveillance and target tracking. As with many other information technologies, wireless sensor networks originated primarily in military-related research. Then coming to the structural and systemic monitoring. Structural systemic monitoring is the another class of application for sensor networks pertaining to monitoring the conditions of civil structures such as the buildings, bridges, and roads, even aircrafts. At present, the health of such structures is monitored primarily through manual and visual inspections or occasionally through expensive and time-consuming technologies such as X-rays and ultrasound. Next, coming to the industrial and commercial network sensing. In industrial manufacturing facilities, sensors and actuators are used for process monitoring and control. Mainly in a multi-stage chemical processing plant, there may be the sensors placed at different points in the process in order to monitor the temperature, chemical concentration, and pressure. Mainly in the chemical processing, we are using the sensors. The main key design challenges, what are the main key design challenges we are facing is extended lifetime. As mentioned above, WSN nodes will generally be severely energy constrained due to the limitations of batteries. Then coming to the responsiveness, a simple solution to extending network lifetime is to operate the nodes in a duty cycle manner with periodic switching between sleep and wake up modes. Coming to the robustness, the vision of wireless sensor networks is to provide large scale at fine grained coverage. This motivates the use of large numbers of inexpensive devices. However, inexpensive devices can often be unreliable and prone to the failures. Coming to the synergy. Moore's Law type advances in technology have ensured that device capabilities in terms of processing power, memory, storage, radio transceiver, performance, and even accuracy of sensing improve rapidly. Coming to the scalability, so these are the main design challenging. For many envisioned application, the combination of fine granularity sensing and large coverage area implies that wireless sensor networks have the potential to be extremely large scale. Heterogeneity. There will be a heterogeneity of device capabilities in realistic settings. This heterogeneity can have a number of important design consequences, for instance. The presence of a small number of devices of higher computational capability along with a large number of low capability devices can indicate a two-tier cluster-based network architectures. Then the key design challenge coming to the seventh point is self-configuration. Because of their scale and nature of their applications, wireless sensor networks are inherently unattended distributed systems. Autonomous operation of the network is therefore a key design challenge. From the very start, nodes in a wireless sensor network have to be able to configure their own network topology. Coming to the self-optimization and adaptation. Traditionally, most engineering systems are optimized a priori to operate efficiently in the face of expected or well-modeled operating conditions. And next, coming to the 9 point systematic decision. As we see, wireless sensor networks can often be highly application specific. There is a challenging trade-off between ad hoc narrowly applicable approaches that exploit application specific characteristics to offer performance gains and more flexible, easy to generalize. Coming to the privacy and security, the large scale prevalence and sensitivity of the information collected by wireless sensor network give rise to the final key challenge of ensuring both privacy and security. Wireless sensor networks are equipped with the deployment targets also. The problem of deployment of a wireless sensor network could be formulated generically as follows. Given a particular application context, an operational region, and a set of wireless sensor net devices, how and where should these nodes be placed? A number of basic questions must be considered when deploying a wireless sensor network. Structure versus randomized deployment. Does the network involve structural placement or randomly scattered deployment? And over deployment versus incremental deployment. And coming to the third one is network topology. Coming to the fourth point is homogeneous versus heterogeneous deployment and the coverage metrics. First, we can differentiate the structural versus randomized deployment. Actually, in the randomized deployment approach is appealing for futuristic applications of a large scale where nodes are dropped from aircraft or mixed into concrete before being embedded in a small structure. The small medium scale double-Asian are likely to be deployed in a structured manner. We have to take the wireless sensor networks in a structured manner via the careful hand placement of the network nodes. These are the 3 points we are using in the structured nodes. placing or gateway device at a location that provides the desired wide network and power connectivity. Place sensor nodes in a prioritized manner at locations of the operational area where sensor measurements are needed. If necessary, add additional nodes to provide requested network connectivity. Coming to the second step can be challenging if it is not clear exactly where sensor measurements are needed, in which case a uniform or grid-like placement could be best choice. Next, coming to the network topology. The communication network can be configured into several different topologies. First one is the single hop star. The simplest double-station topology is the simple hop star issue. Is displayed in the figure. Every node in this topology communicates its measurements directly to the gateway. Yes, but in the multi-hop mesh and grid for larger areas and networks, multi-hop routing is necessary. Next, coming to the two-tier hierarchical cluster, perhaps the most compelling architecture for double-station is a deployment architecture where multiple nodes within each local region report to different cluster heads. These are the network topology, single hop technology, hope topology, and then multi-hop topology. Third one is a sector grid, and fourth one is a two-tier hierarchical cluster topology. And coming to the connectivity in geometric random graphs, the connectivity and coverage metrics will be where properties of random deployments can be best analyzed using random graph theory. Mainly, the random graph model is essential, a systematic description of some random experiment that can be used to generate graph instances. These are the Bernoulli random graphs. Studied in traditional random graph theory are formed by taking n vertices and placing random edges between each pair of vertices independently with probability P. And coming to the connectivity of the wireless sensor networks, mainly the connectivity will be taken place in the probability of network connectivity, whereas as the radius parameter R of a geometric graph, random graph is varied. Depending on the number of nodes n, there exists different critical radii beyond which the graph is connected with high probability. These are the graphs shown in the wireless sensor networks connectivity. These are the three graphs we have taken place. We have seen in this one, in these three figures. It's coming to the monotone properties. The monotonically increasing property is any graph property that continues to hold if additional edges are added to a graph that already has the property. A graph property is called monotone. If the property or its transfers are monotonically increasing, nearly all graph properties of interest from a networking perspective such as K connectivity, hamiltonicity, K colorability, etc. are monotone. A key theoretical research pertaining to geometric random graphs are monotone property shows critical phase transitions. Then coming to the connectivity and coverage in grid. Another geometric random graph model is the unreliable sensor grid model. In this model, n nodes are placed on a square grid within a unit area. P is the probability that a node is active. These are the three steps we are seeing for the active nodes to form a connected topology. We are using the O of log n by n. The maximum number of hopes required to travel from any active node to another O is root of n by log n. There exists a range of p values sufficiently small such that the active nodes form a connected topology but do not cover the unit square. Next, coming to the connectivity using power control. Regardless of whether randomized or structured deployment is performed, once the nodes are in place, there is an additional tunable parameter that can be used to adjust the connectivity properties of the deployed network. This parameter is the radio transmission power setting for all nodes in the network. It can extend the communication range, increasing the number of communicating neighboring nodes and improving connectivity in the form of availability of end-to-end paths. For existing neighbors, it can be improved in quality. It can induce additional interference that reduces capacity and introduces congestion. It can cause an increase in the energy expended. Most of the literature on power-based topology control has been developed for general ad hoc wireless networks, but these results are very much central to the configuration of WSN. Coming to the minimum energy connected network construction. Normally, we can consider the problem of deriving a minimum power network topology for a given deployment of wireless sensor nodes that ensures that the total energy usage for each possible communication path is minimum. A graph topology is defined to a minimum power topology. If for any pair of nodes there exists a path in the graph that consumes the least energy compared with any other possible path. The construction of such a topology is the goal of the minimum energy communication network algorithm. There are different types of topologies we are seeing in the wireless sensor networks. However, it turns out the MECN algorithm does not necessarily connect a topology with the smallest number of edges. Let's see, U of V is the U comma V is the energy cost for the direct transmission between nodes. U and V in the MECN generated topology. It is possible that there exists another route or between these very nodes such that the total cost of routing on the path is C of or less than should be C of U comma B. Coming to the minimum power, common power setting. The combo protocol ensures that the lowest common power level that ensures maximum network connecting is selected by all nodes. A number of arguments can be made in favor of using a common power level that is as well as the possible. Then coming to the Campo algorithm can be shown to provide the lowest functional common power level for all nodes in the network. Next are the connectivity of the WSN. We have to minimize the maximum power. Work by Ramanathan Hussain presents exact as well as the heuristic algorithm that seek to generate a connected topology with non-uniform power level such that the maximum power level among all nodes in the network is minimized. The cone-based topology network. Mainly, the cone-based topology network provides a minimal direction-based distributed route to ensure that the whole network topology is connected. CPTC construction is illustrated mainly in the figure. On the left, we can see the intermediate power level for a node, at which there exists an alpha cone in which the node does not have an neighbor. This is the construction diagram of the cone-based topology control. These are the coverage metrics. Connectivity metrics are generally application independent. In most networks, the objective is simply to ensure that there exists a path between every pair of nodes. At most, if robustness is a concern, the K connectivity metric may be used. However, the choice of coverage metric is much more diverse and depends highly upon the application. This is the K coverage. This metric is applicable in context where there is some notion of a region being covered by each individual sensor. Here we have taken one of the example. We have taken the consider operating region A with n sensors. We are taking one region and the number of n sensor nodes should be the n. We can take the K coverage entire region. This is the entire region coverage. Path observation. Using a dynamic programming algorithm, determine the path between the starting and ending nodes of the graph that maximizes the lowest cost edge transferred. These are the graphs. Maximal breach path through Varnish cell and edges, and minimal support path through delaying technologies. These are the two paths we are using. Next, coming to the localization of the wireless sensor networks. Here we are using the localization techniques. The main techniques for the localization of the wireless sensors, it provides location stamps. How it can locate and track point objects and monitor the spatial evolution of a diffuse phenomenon to determine the quality of coverage to achieve load balancing, to form clusters to facilitate routing to perform efficient spatial varying. Main key issues. What are the key issues we have to find out in the localization? What to localize? What is the meaning of localization? If we want to create any nodes at the sensor networks, that nodes should be localized in some particular place. This place we have to find out where what to localize and when to localize, how well to localize, where to localize, and how to localize. Then localization approaches. Coarse grain localization using minimal information. And fine grain localization using detailed information. Coarse grain node localization using minimum information. Binary proximity is the one kind of the technique we are using in the localization. Centroid calculation and geometric constraints. And coming to the localization using intersection of geometric constraints and upper bounds on these regions are tight. The accuracy of this geometric approach can be further enhanced by incorporating. Coming to the approximate point in triangle, identifying the codes. Fine grained node localization using detailed information. Distance estimation using time differences. Triangulation using distance estimations. These are the localization techniques we are seeing. Angle of arrival. Another possibility for localization is to angular estimates instead of distance estimations. Pattern matching. These are the pattern matching techniques. RF sequence coding and network-wide localization issues. So far we have discussed on the problem of node localization, which is that of determine the location of a single unknown node given a number of nearby references. Coming to the constraint based techniques. These are the RSS based joint estimation, iterative multi-alteration. Iterative multi-alteration technique is applicable whenever inter-node distance information is available between all neighboring nodes.